Hello, good morning to all of you. We are discussing about the basis sets after the ab initio Hertzberg method, and in basis sets you know that this is the a combinations of basis function that is actually linearly combined to express the molecular orbitals. Okay, so here in this lecture also we will continue our discussion a little more about the basis sets. So you now can understand that Rutherford version of the Hertzberg equation is obtained by substituting the molecular orbitals wave function in the Hertzberg equation by linear combination of some basis functions, which is actually expressed as like C1 phi 1 plus C2 phi 2, where phi is the weightage, phi is the wave function, and C is the weightage of that particular. Phi is the basis function and C is the weightage of that basis function. And Rutherford equations actually provides the values of all C's, means that all the coefficients and the molecular orbitals wave function and the molecular energy levels epsilon. So the overall electron distribution in the molecule can be calculated from the total wave function psi. So after linearly combined, you will get the total wave function, and the total wave functions you can get the total molecular energy as well as the electron distribution. So and from the in principle any property can be calculated from the psi. Okay. Also psi can be actually written as a Slater determinant of the component special wave functions. Psi, small psi, by including spin function also, and any property of a molecule can also be calculated from both of them. The component wave function psi and their energy levels epsilon are actually extremely useful. Why? Because these two are actually expressing the molecular orbitals, and you know that as a chemist we always want to see the shape and the energies of the molecular orbitals, like for HOMO and LUMO, because the electron transfer and other mechanisms can take place for the transformation of electrons from HOMO LUMO or like that. So this is a pictorial representation of basis functions that we can use in our calculations. So if you like take 4 basis functions and if you combine them linearly, then what you can get, you will get the total 4 molecular orbitals with the energies epsilon 1, epsilon 2, epsilon 3, epsilon 4, and if these are oriented with the energy, then you will get these 4 orbital have a different energy. And if there are 4 electrons in the molecule, then only psi 1 and psi 2 will be occupied, and this psi 3 and psi 4 will be partial. Okay, and the Slater determinant can be, because this psi 1 is a special orbital, it has 2 spin orbital alpha and beta psi 1. So we can write the Slater determinants for these cases. Again we will get this type of Slater determinant when the first row is for electron 1, second is for electron 2, third is for electron 3, and 4 is for electron 4. So in the Slater determinant, row is for the electrons and the column is for the orbital, because you can see here all are for psi 1. So psi 1 is an orbital and this is for column. And this actually started from phi 1, phi 2, phi 3, phi 4, 4 basis functions were linearly combined. Okay. So now let's make a summary about the basis set. So a basis set is a set of mathematical functions that we actually call basis functions that linearly combined to yield the molecular orbitals. The functions are usually centered on atomic nuclei. This is atom-centered basis set. So approximating molecular orbital as linear combination of basis function usually called the linear combination of atomic orbital approach that we used in earlier. Although the functions are not necessarily, here the basis functions, these functions are not necessarily conventional atomic orbitals, but they can be any set of mathematical functions that are convenient to manipulate and which in linear combinations give useful representations of the molecular orbitals. So with this reservation, linear combination of atomic orbital is a useful acronym, and physically these basis functions describe the electron distribution around an atom, and combining atomic basis functions actually will get the electron distribution in the molecule as a whole. So now we are saying so many times that basis function, and these basis functions are, we are also said this is any type of mathematical functions, because we do not have any prototype for the molecules. Like in atom we have for the prototype like hydrogen atomic orbitals. So this what type of functions can be useful in these calculations to describe accurately the electron distributions phenomena. So the electron distribution around the atom can be represented in several ways. Like in hydrogen-like functions based on solutions of the Schrodinger equations for the hydrogen atom, we can use polynomial functions with adjustable parameters. We can use Slater functions. We can use Gaussian functions, and we will discuss little more about these sequentially. So Slater and Gaussian functions are the most useful, most commonly used basis functions due to mathematical simplicity here. So now let's see what are the Slater type of basis functions, because you have already seen hydrogen-like wave functions that we are not used for molecules, and we used the Slater type of functions, but these functions also actually use the hydrogen type functions concept, like that if we use the mathematical form of the normalized Slater type orbital, this phi can be expressed as 2 zeta to the power n plus half n factorial to the power half r to the power n minus 1 to the power minus zeta r y lm theta and phi. And this is looks very complicated expressions, but you don't need to remember everything. You just remember that this phi actually varied exponential zeta part. Okay, so it's depends on the one exponential negative zeta, and this zeta is an exponent can be chosen according to a simple set of rules developed by Slater that depend among other on the atomic number n, principal quantum number, valence orbital, and the spherical harmonics functions like y, lm, theta, phi. Okay. So these all are actually familiar from the solution of the Schrodinger equation for the hydrogen atom. If you remember that this type of e to the power minus zeta r type of functions are also we found in hydrogen atom type orbitals when we solved the Schrodinger equations for hydrogen atom. Okay. So this is basically extrapolated understanding from the hydrogen type of atomic orbital, but exactly this is not the hydrogen atom orbital. So what is the advantage and disadvantage of this type of orbitals, this type of basis functions? So if you remember, if you see these functions and if you plot phi with respect to r, then you can see that your at when r is 0, your functions, basis functions, value of the functions will be very high, and when r is becoming higher, as this is exponential decaying functions is defining exponential decay, your functions will be the value of the functions will fall very fast. Okay. So it says this is actually able to explain the phenomena of the orbitals, because if you remember the plot of the hydrogen atomic orbitals, it has the maximum value at the nucleus, but it is suddenly decrease when we go beyond from the nucleus. So it's actually it's said a cusp at the nucleus, that is it is not smooth, it immediately falls the value of the functions, or immediately falls the electron density when we go beyond, we go far from the nucleus. So actually the shape of the molecules, shape of the orbitals are very accurately, almost very accurately represented by this Slater type of orbital. But the most severe problem which have this type of orbital, because STOs have very significant limitations, because it is extremely excessive computer time is required for these calculations, because there are no analytical solutions available for the general integral which arises in Hartree-Fock equations. If you know that when we solve the Hartree-Fock equations, we get so many integral terms, And if we use the Slater-type orbitals, then we cannot solve this that integrals using in analytical ways. So we have to follow the numerical integrals. For that, numerical methods we have to follow, and in the due to these numerical methods, that calculations need so much time. So actually, practically, it's very tough to use this type of orbitals due to its requirement of excessive computer time. So in the next class, we will define another type of orbitals, which will be more easy to use, and we can get the analytical solutions. And that type of orbitals are called Gaussian type of orbitals. Okay. So thank you very much for now.